There's a video going around claiming that Grok, the AI chatbot built by Elon Musk's company xAI, was asked about Google's quantum chip and revealed something so shocking it demands your attention. Before we go any further, let's be honest about what's actually behind that claim, because it matters for how you should read everything that follows. There's no published transcript anywhere of a specific, verifiable Grok conversation, containing some unique, previously unknown revelation about Google's quantum computing program. What you'll find instead, if you go looking, is a cluster of similarly titled videos, each promising a shocking answer, none of them citing an actual checkable source. That's worth sitting with for a second, because it tells you something useful right away. If Grok had genuinely revealed something new and startling about a Google product, that would be a real story covered by real tech journalists, not something confined to a single recycled video format with no attached evidence. But here's why this is still worth your full attention, and why I think the honest version of this story actually delivers on the promise of the title, just not in the way the fake version wants you to expect. If you actually opened up Grok right now and asked it a serious, detailed question about Google's quantum chip, Willow, it would give you a genuinely accurate, well-organized answer, drawing on the same extensive public record of real, verified information that any well-informed person could access themselves. And that real information turns out to be plenty shocking on its own once you understand it properly. No invented chatbot mystery required. So let's do exactly that. Let's walk through what's actually verifiably true about Willow, the way a careful, well-sourced answer would lay it out. And along the way, let's be honest about what an AI chatbot can and can't meaningfully add to a story like this one. Willow is Google's newest quantum processor, unveiled in December of 2024 at the company's quantum computing lab in Santa Barbara, California. It's a superconducting quantum chip built from 105 qubits, cooled inside a specialized refrigerator to a temperature colder than the emptiest regions of outer space, because even the smallest trace of ordinary heat is enough to destroy the fragile quantum states the whole system depends on. Google ran Willow through a specific, deliberately brutal benchmark called random circuit sampling, a task built to be almost impossibly hard for a classical computer, while remaining natural for a quantum one, and the chip completed that computation in under 5 minutes. According to Google's own published estimate, the same task would take the world's fastest classical supercomputer approximately 10 septillion years, a number so large it exceeds the age of the universe many times over, a claim that was picked up by Reuters, published in the peer-reviewed journal Nature, and confirmed on the record by Hartmut Nevin, the head of Google Quantum AI, in interviews with established outlets. Google's CEO Sundar Pichai called it a result that cracked a 30-year challenge in the field. And the announcement drew public reactions from figures like Sam Altman, who congratulated the team, and Elon Musk, who simply replied, "Wow," to Pichai's post about it. A detail worth noting, given that this entire story is now being filtered back to you through Musk's own AI chatbot. That 30-year challenge Pichai referenced is worth explaining properly, because it's genuinely the more important part of the Willow story, even though it doesn't generate quite as dramatic a headline number as the 10 septillion year comparison does. Quantum computers have always faced a brutal, self-defeating problem. Qubits are extraordinarily fragile, easily disrupted by heat, electromagnetic interference, or even a stray cosmic ray. And for decades, adding more qubits to build a more powerful machine also meant adding more sources of error, making the overall system less reliable rather than more. Theorists had proposed since the 1990s that this didn't have to be true, that a properly designed error-correcting scheme called a surface code should be able to reverse that relationship entirely, making a system more reliable as it scaled up, provided your individual qubits were good enough to cross a specific calculable threshold. Willow was the first system to demonstrate this cleanly, showing a logical error rate that dropped in a predictable exponential curve, as researchers scaled up the size of the error-correcting lattice, exactly matching the 3-decade-old theoretical prediction. Nevin summarized the moment plainly in an on-record statement. "We are past the break-even point." That's a real, quotable, independently confirmed milestone, published with full technical detail for other scientists to scrutinize, precisely the opposite of a mysterious, unsourced chatbot revelation. There's more to the real story too, and it gets stranger the further you go, which is exactly why it doesn't need any embellishment. In October of 2025, Google's Quantum AI team published a follow-up result using Willow, an algorithm called quantum echoes, detailed in a paper in Nature. This experiment measured something called an out-of-time order correlator, essentially a way of tracking how a tiny, deliberate disturbance introduced into a scrambled, chaotic quantum system can be traced back out again afterward, like sending a whisper into a hurricane and picking out its echo on the other side. According to Google, the algorithm ran roughly 13,000 times faster than the best available classical algorithm running on top supercomputers. And crucially, unlike some earlier quantum computing demonstrations, this result was described as verifiable, meaning it could, in principle, be reproduced on a different quantum computing platform entirely. A genuinely important detail because it addresses a common and legitimate criticism of earlier quantum advantage claims that they were sometimes difficult for anyone outside the original team to independently confirm. Tom O'Brien, a Google quantum AI researcher, said on the record that this verifiability represented a meaningful step toward bringing quantum technology into real, mainstream practical use. This measurement connects, in a genuinely fascinating way, to some of the deepest open questions in theoretical physics, including how information behaves inside black holes and how quantum randomness in the earliest instance after the Big Bang may have seeded the structure of the universe we see today. Real, peer-reviewed physics that touches on some of the biggest questions humanity has ever asked. No invented drama required to make it interesting. And then there's the part of the real Willow story that's genuinely controversial, in a way that's worth explaining carefully because it's the closest thing to an actual shocking claim anywhere in this narrative, and it comes directly from Google itself, not from any anonymous or fabricated source. In that same December 2024 announcement, Nevin wrote that Willow's extraordinary performance lends credence to the notion that quantum computation occurs in many parallel universes, explicitly crediting physicist David Deutsch's many worlds interpretation of quantum mechanics, a real, decades-old, seriously debated position within physics, championed by a genuinely important figure in the actual history of quantum computing theory. Under this interpretation, first proposed by physicist Hugh Everett in the 1950s, every possible outcome of a quantum measurement genuinely occurs, but each different outcome plays out in its own separate branching universe. And Deutsch's specific argument is that quantum computers derive their power by performing calculations across many of these parallel branches simultaneously. It's a real, legitimate scientific position, but it's also a minority one, and plenty of serious physicists pushed back on Nevin's framing directly and publicly, pointing out that the far more mainstream Copenhagen interpretation of quantum mechanics explains exactly the same underlying mathematics, the same interference effects that make Willow's speed possible without needing to invoke any parallel universes at all. Both interpretations predict the exact same measurable result from Willow's experiment, which is precisely why physicists describe this as a genuinely open interpretive question rather than something Willow's raw performance could resolve one way or the other. That's a real scientific controversy, expressed by a named person in an official company blog post, and it's about as close as this story legitimately gets to shocking, in the sense that it's a real, still unresolved debate about the fundamental nature of reality itself, touched off by a real piece of hardware. Now here's where I want to be genuinely useful about the Grok part of this headline, because I think there's a real honest and interesting point buried underneath the fabricated framing. If you actually asked Grok, or any other capable AI chatbot, a detailed question about Willow, you would very likely receive a response touching on most or all of what we've just walked through. The error correction milestone, the speed benchmark, the quantum echoes result, and even Nevin's multiverse comment and the resulting scientific pushback, because these are exactly the well-documented, widely published facts that a well-trained AI model would have absorbed from its training data, drawn from the same public record of Nature papers, Reuters articles, and on-record company statements that any careful human researcher could access as well. That's a genuinely useful thing an AI chatbot can do, synthesizing a complex, multi-year, multi-source technical story into a single, coherent, accurate answer on demand in seconds. It is not, however, the same thing as an AI chatbot possessing secret, privileged knowledge about Google's internal quantum computing program that no human researcher has access to, or generating some brand new discovery about Willow that didn't exist in the published record before you asked the question. Large language models like Grok generate responses by drawing on patterns learned from the text they were trained on, not from any live, exclusive connection to Google's actual internal lab data. And they have no mechanism for independently verifying or generating genuinely new experimental results about a piece of hardware they've never had any direct access to. This distinction is worth sitting with a little longer, because it explains exactly why the shock you framing in this specific video title doesn't hold up, even though the underlying facts about Willow genuinely are remarkable. A real scientist, or a well-informed member of the public, hearing an AI chatbot accurately summarize Willow's error correction breakthrough or its quantum echoes result wouldn't be shocked by the chatbot itself, because these are already well-publicized, widely reported facts, covered by Reuters, the BBC, and dozens of other outlets over the past year and a half. What might genuinely impress someone is how quickly and coherently an AI model can pull together a scattered, technical, multi-source story into a single clear answer, which is a real and legitimately useful capability, just a considerably less dramatic one than an AI revealed a shocking secret. and a capability that says more about how well organized the underlying published information already is than about any special insight the chatbot itself possesses. It's worth being fair to the genuinely impressive parts of the real story one more time, because they deserve to stand on their own without needing an AI chatbot as a framing device at all. Chaoyang Liu, a quantum physicist at the University of Science and Technology of China, told Nature directly that Willow's error correction result represented a truly remarkable technological breakthrough. A real, on-record assessment from an independent scientist working at a rival institution. Exactly the kind of outside validation that gives a scientific claim real credibility. Google also addressed, directly and transparently, a legitimate criticism that had dogged its earlier 2019 Sycamore supremacy claim, when IBM researchers had argued that improved classical algorithms could complete the same benchmark task in about 2.5 days rather than the originally claimed 10,000 years. In its Willow announcement, Google stated that even under the most idealized classical computing conditions, a classical machine would still need 1 billion years to match Willow's performance on the new benchmark, a considerably more conservative and better defended estimate than the company's earlier claim, directly incorporating the lessons of that earlier scientific pushback rather than ignoring it. He even also gave a notably candid, on-record answer to the BBC about realistic timelines, stating plainly that genuinely commercial applications of quantum computing were still not expected before 2030 at the earliest, a refreshingly grounded, unhyped admission from the very executive whose own company had just delivered the headline-grabbing announcement. There's also real, ongoing, competitive context worth including, because a full, accurate answer to what's going on with Google's quantum chip would naturally include it, and a good AI chatbot response would too. Google isn't operating in isolation. IBM continues pursuing its own aggressive quantum roadmap, prioritizing higher raw qubit counts across chips like its Condor processor. China's Zhuchangji program, based at the University of Science and Technology of China, the same institution Chaoyang Liu works at, announced its own below-threshold error correction milestone in a similar timeframe, using a different control architecture than Google's, providing an independent confirmation that this broader category of breakthrough isn't a fluke tied to one specific lab's hardware quirks. Quantinuum, working with an entirely different qubit technology based on trapped ions rather than superconducting circuits, has posted its own competing benchmark results as well. Bitcoin enthusiasts, meanwhile, reacted to the Quantum Echo's announcement with a pointed, entirely public question, directly asking Google's own AI account on social media whether the new algorithm posed any threat to the specific cryptographic method, SHA-256, that secures Bitcoin's blockchain, a real, documented, slightly humorous moment of public skepticism that shows exactly how openly and publicly these claims get scrutinized and stress-tested by outside observers the moment they're announced, rather than being quietly whispered about in some closed, unverifiable setting. So let's bring this all the way back to the actual question posed by the headline. What would Grok, or any honest, well-informed source, actually reveal if you asked it about Google's quantum chip? 105 qubits, cooled colder than deep space. A benchmark computation completed in under 5 minutes that would take a classical supercomputer, by Google's own more conservative later estimate, 1 billion years to match, and by its original estimate, 10 septillion years. A 30-year-old theoretical threshold in error correction, finally crossed and independently confirmed by outside physicists. A follow-up experiment, Quantum Echoes, that's genuinely, verifiably 13,000 times faster than the best classical alternative, and touches on real, serious open questions about black holes and the origins of cosmic structure. And a genuinely unresolved, actively debated philosophical controversy about whether all of this is best explained by parallel universes or by considerably more conventional quantum mathematics. A debate initiated by Google's own lead researcher and pushed back on by physicists across the field. That's the real answer, the one grounded in Nature publications, on-record interviews, and independent expert commentary, rather than an unsourced, unverifiable chatbot conversation dressed up as a secret revelation. If there's a genuine, worthwhile shock to take away from all of this, it's simply this. The real story was always strong enough to stand entirely on its own without needing a fictional chatbot conversation to make it feel important. Willow's actual documented achievements, verified by peer review, confirmed by named researchers, and independently validated by rival institutions, are already among the most significant developments in quantum computing in years. The next time a video promises that some AI chatbot revealed something shocking about a real scientific breakthrough, the most useful question to ask isn't what the chatbot supposedly said. It's simply this. What does the actual published record say? Who said it on the record, and can I go check it myself? In this case, once you do exactly that, you find a story genuinely worth your attention, no invented mystery required, and no chatbot conversation necessary to make it feel real because it already is. Let's go a little deeper into the actual mechanics of Willow's error correction breakthrough because it deserves a fuller explanation than a single summary paragraph can give it, And it's genuinely the most technically important part of this entire story. Every physical qubit in a quantum processor is inherently noisy, subject to disruption from heat, electromagnetic interference, and even the occasional cosmic ray passing through the chip. The solution theorists proposed decades ago, called a surface code, takes many individually unreliable physical qubits and weaves them together into a single, considerably more robust logical qubit, arranging them in a lattice where some qubits hold information and others continuously check their neighbors for signs of error, all without ever directly reading out the protected information itself, since directly measuring a qubit would collapse its fragile quantum state and destroy the very information the whole scheme is trying to protect. The math predicted that if your physical qubits were good enough, sitting below a specific calculable error threshold, then adding more of them to this correcting lattice should make your logical qubits' reliability improve exponentially. The bigger the lattice, the better the protection. Below that threshold, scaling up helps enormously. Above it, scaling up actively hurts, adding more components and more chances for something to go wrong. For roughly 30 years, this was a beautiful piece of theoretical physics that nobody had cleanly, unambiguously demonstrated on real hardware. Willow changed that, showing a logical error rate that dropped in a clean, predictable curve as researchers increased the size of the correcting lattice, matching the decades-old prediction closely enough that independent physicists, including Chao-Yang Liu at a rival Chinese institution, were willing to publicly call it remarkable. It's worth spending a moment on why this particular achievement matters more, in practical terms, than the flashier 10 year speed comparison that dominates most headlines about Willow. A single narrow speed benchmark, however dramatic, doesn't by itself tell you whether quantum computers can ever be reliably scaled up to solve broader, more practically useful problems, the kind involving drug discovery, materials science, or fusion energy research that Pichai referenced in his own comments about Willow's long-term potential. The error correction result addresses that deeper question directly because it tackles the exact reason quantum computing has taken so long to move from laboratory curiosity toward genuinely useful technology. Without a working solution to the scaling versus reliability trade-off, building bigger, more capable quantum computers was, for decades, a fundamentally losing battle, adding qubits while adding errors faster than you could ever hope to correct them. Willow's demonstration that this trade-off can be beaten with real, independently verifiable, exponentially improving results is arguably the single most consequential piece of the entire announcement, even though it doesn't generate quite as viral a headline number as the speed comparison, and considerably less attention than an entirely invented chatbot mystery layered on top of it. There's also real value in being precise about what verifiable actually means in the context of the quantum echoes result, because it's a detail that often gets glossed over, but genuinely matters for evaluating how seriously to take the underlying claim. Some earlier quantum computing demonstrations faced a legitimate scientific criticism. Because the calculations involved were so complex, it was difficult for anyone outside the original research team to independently confirm that the reported results were actually correct, since no classical computer could feasibly check the answer by brute force, and no other quantum computer existed with the exact same configuration to cross-check against. The quantum echoes result was specifically designed to sidestep that problem, structured so that its correctness could, in principle, be confirmed by running the same experiment on an entirely different quantum computing platform and comparing results, giving the broader scientific community a genuine, independent way to check Google's work, rather than simply having to trust the original team's own internal verification. That's precisely the kind of methodological rigor that distinguishes a legitimate, peer-reviewed scientific claim from an unverifiable one, and it's exactly the kind of detail that never appears in any fabricated chatbot revealed a secret video, because acknowledging that level of careful, checkable methodology doesn't fit the dramatic, mysterious framing those videos depend on. It's also worth placing this entire Willow story inside the broader, ongoing competitive landscape of quantum computing research, because a complete, honest answer to what's happening with Google's quantum chip naturally includes that wider context. And it's exactly the kind of detail a genuinely well-informed AI response, or a genuinely well-informed human explainer, would include as well. IBM continues to pursue a somewhat different strategic emphasis, prioritizing higher raw qubit counts across processors like its Condor chip, betting that shear scale combined with its own error mitigation techniques will eventually deliver practical quantum advantage, even before every theoretical error correction threshold has been perfectly crossed. China's Zhuchangji program, based at the University of Science and Technology of China, announced its own below-threshold error correction milestone in a broadly similar timeframe to Willow's announcement, using a notably different control architecture. An all-microwave approach rather than Google's mixed control scheme, providing a genuinely valuable independent confirmation that this general category of breakthrough isn't some fluke specific to one lab's particular hardware quirks. Quantinuum, pursuing an entirely different underlying qubit technology built on trapped ions rather than superconducting circuits, has published its own competing benchmark results as well, adding yet another independent data point to the broader picture. None of this competitive richness ever makes it into the fabricated chatbot revealed a secret genre of video, because acknowledging a well-documented multi-company, multi-technology scientific race doesn't fit neatly into a story built around one isolated, unverifiable claim from a single, unnamed source. There's a genuinely amusing, entirely real detail worth including here too, because it's exactly the kind of texture that shows how openly and publicly these claims get scrutinized the moment they're made, in sharp contrast to the closed, secretive framing a fabricated video wants you to imagine. When Google announced the Quantum Echoes result, cryptocurrency enthusiasts immediately and publicly asked Google's own AI account on social media whether the new algorithm posed any threat to SHA-256, the specific cryptographic hash function that secures Bitcoin's entire blockchain, a real, documented, slightly cheeky moment of public accountability that shows exactly how quickly outside observers, with their own strong incentives to scrutinize the claim carefully, jump in to stress test a big scientific announcement the moment it's made. That's what real scientific scrutiny actually looks like in the modern era. Immediate, public, occasionally a little irreverent, and entirely traceable. A world apart from a story that depends on a single, unverifiable, secondhand chatbot conversation with no public record anywhere. So if you take one thing away from this whole discussion, beyond just the specific facts about Willow, let it be a simple, transferable habit. When a video promises that an AI chatbot revealed something shocking about a real company's real technology, the useful next step isn't to wonder what mysterious secret the chatbot supposedly uncovered. It's to go looking, yourself, for the actual underlying published record, the peer-reviewed paper, the on-record interview, the independent expert commentary from a rival institution, exactly the kind of sourcing that turned out to back up every genuinely remarkable claim about Willow we've walked through today. If that record exists, and it's detailed, consistent, and traceable to named people and named publications, you're looking at a real story, one that was almost certainly already reported by legitimate outlets well before any recycled chatbot video got around to repackaging it. If that record doesn't exist, no matter how many videos repeat the same dramatic claim with slightly different wording, you're looking at exactly what a fabricated story is built to feel like. Mysterious, exciting, and once you actually go check, entirely empty. And that's really the honest, full answer to the question this title asked. What would Grok, or any careful, well-informed source, actually reveal about Google's quantum chip? Not a secret, not a hidden warning, just the real, documented, independently verified story. 105 qubits, cooled colder than space, crossing a threshold physicists had been chasing since the 1990s, running an algorithm 13,000 times faster than the best classical alternative, verified in a way that lets other labs check the work, and wrapped around a genuine, still unresolved debate about whether the universe is quietly splitting into countless branches every time the chip runs. That's the whole story, and it was sitting there in plain sight, published, on the record, and available to anyone willing to go read it, long before anyone decided to package it as a chatbot's shocking secret.